So today we have with us Professor Sanjit Mitra from IUCA Pune. And it's a pleasure to have him here talking about LIGO-India. He completed his PhD from IUCA in 2006 and had a couple of postdocs at Côte d'Azur Observatory in France and then JPL in Caltech, US. He also spent some time at University of California, Santa Barbara, working on the Planck mission. He then joined IUCA as an assistant professor in 2011, where he is currently a professor. His research spans over observational astronomy, both in gravitational waves and cosmic microwave background, with dealing with current and upcoming gravitational wave detectors, systematic effects analysis strategies in the CMB analysis, and employing high-performance computing in various data-driven scenarios. And over the span of his research career, he has several accolades that includes JPL NASA Team Star Award for outstanding contribution to Planck, a breakthrough prize in fundamental physics for the detection of gravitational waves as part of LIGO scientific collaboration, and Gruber Cosmology Prize for mapping the CMB anisotropies as part of the Planck team, amongst various others. And he has been very deeply involved in LIGO-India project since the very inception. And he's currently LIGO-India project coordinator at IUCA and the science spokesperson for LIGO-India. So today we will hear from him about science with LIGO-India, immediate opportunities and exciting possibilities. So with that, please take it away.
Thank you very much for inviting me here. It has been a wonderful visit so far. I wish I could visit for longer. Can you hear me properly? Okay. So in this presentation, I actually had too much content because there are too many exciting science going on in LIGO-India, but then it is very tempting to say what I am doing also. So I have somehow combined both of these, and hopefully you will be able to survive. Okay, so I'll go straight away to the business. So this is the, many of you have probably seen this picture, that the merger of two black holes which the signals were detected in two detectors 3,000 kilometers away, and this was the first detection of gravitational waves, direct detection of gravitational waves, and this essentially marks the beginning of a new field of astronomy. And for this, these three gentlemen got the Nobel Prize in Physics, but then there are more than 1,000 people all over the world who contributed to this activity, and it was a remarkable display of international collaboration. And significant contribution came from India in various institutes like IUCA, RRI, and many other places. And I don't want to list all of them, but we can get into this later on. This includes theoretical work, data analysis, and partly instrumentation as well, even though we are now moving more into the instrumentation part. Now, after 5 years or so of GW astronomy, this was the situation. Okay. Now, and you won't be wondering like why I'm showing this curve, this plot, or whatever, periodic table. The thing is that in 2015, when this whole exercise of advanced LIGO was starting, our primary question was that what if advanced LIGO does not detect anything? And many of us were concerned that how I went to the extent of telling, giving a talk like this and then telling students, that we are using this Michelson interferometer, which is a great example of a null experiment, that it did not detect anything, and see, it changed the world. And maybe if gravitational waves are not detected, then maybe the new physics will come. But now today here we are, almost 8 years are done, and like we are approaching, we have essentially made 100 detections, and people are looking forward to hundreds of detections, and people are thinking when we are reaching 1,000 and things like that. Okay, so things change pretty dramatically over the last few years, and we would call it a pretty eventful beginning. And you can see the situation right now. There are this 04, the fourth observing run of the LIGO-Virgo-Kagra collaboration started in May, and by now we have 55 significant detection candidates. So you can imagine that many of these, or maybe all of them, would eventually become direct real detections. And this is already more than 50% of what was detected so far in the last few years. So you see that the growth is exponential, meaning if you see that it is proportional to the cumulative time. Now, but this number is also very significant. There are more than 1,000 events which are low significant. A significant part of them, let's say could be 70%, are true signals. And a lot of astrophysics can be done in different ways, say with machine learning. I think the thing is that, and there are various activities are going on in that regard, that without getting into, even though you don't know a specific event is a true detection or not, one could do a lot of science to get the stochastic, statistical properties of these populations. Now, so even with all this, like even if we have detected 1,000 events, it is still the very beginning of gravitational wave astronomy, and there is a long way to go. And this is where LIGO-India is going to play a major role. So these are some of the major unanswered questions, and there are many more which are listed in the Gravitational Wave International Council. It's called GWIC roadmap, but I will read out some of these to say how fundamental they are. So for example, where, when, and how do the black holes and their binaries form? A very fundamental question, and this also leads to all these other questions, that how much bigger black holes, like supermassive black holes form, like with hierarchical merger, or they start from a seed and things like that. How many such black holes are there in the universe? What is the distribution of their masses and spins? This, for example, tells us that whether they are formed in globular clusters, or where in clustered in a dense environment, or in isolated areas where they evolve individually. I'll show a slide on that. How they are distributed in distance and direction, that is, at which redshift do these peak, which will tell us about the star formation rates, etc. And is the distribution isotropic? That is a fundamental question which we will have to address at some point. And as you know, Tarun has mastered this in the CMB domain, but this also have to be done in gravitational waves. It will take a long time, but on the other hand, people have already started writing papers on that. What are the properties of neutron star matter? This is again a fundamental physics question, that what will be the equation of state. There are many right now, but at least with more and more observations, things will become the parameter space will become more constraints. How massive can a neutron star be? Like, can we have a 3 solar mass neutron star, or can we have a 2 solar mass black hole on the other hand? So all these questions are very interesting. Do intermediate mass black holes exist? Well, this was the question before LIGO started, and you can see that we have already detected, I'll show you this here. You can see that 1, 2, 3, 4. So this question is no longer there up to a certain extent. But now the next question is that, are there like few hundred solar mass black holes there? And what is the number? Because then again, they can be linked to see how the bigger black holes form. And then there is general relativity, the ultimate theory of gravitation. That is another very fundamental question. Okay, this can be partly answered with gravitational wave observations. I don't have time to get into this today, so I will tell you right now some ideas that how you could do that. So if we have very sensitive detectors which could detect the final ring down phase with very high signal to noise ratio, see this part, this signal comes after the black hole has merged and it's settling down. So if these ring down modes could be measured with very high signal to noise ratio, then our standard general theory of relativity tells us that those modes are functions of the mass and angular momentum only. If we can see that, then we would know that, okay, it is consistent with general relativity. But in order to know the final mass and spin of the expected mass and spin of the final black hole, we need to get this part with very high signal to noise ratio, because this tells us that what is the what are the masses of the individual black holes and also the spins. I will come to this point again later on, because that will tell us what is the final mass and angular momentum. Okay, so and you know, like, so, and what is the correct value of Hubble constant? I will spend quite a bit of time on this later on. So the thing is that in order to address these questions, a large number of gravitational wave observations are necessary. Yes.
So how do you say whether it's the ultimate theory, and what you're saying is something is consistent with something?
Well, yeah. Let's say that way. I mean, we can never say theory is ultimate, but we can probe at different scales. So this is not the right way to put it. I would say that general theory of relativity is consistent to this particular energy scale would be the right way to put it, but that would sound too technical. But anyway, I'll figure it out how to put it properly. Thanks for pointing it out, because there is nothing like an ultimate theory. Okay, so now what should be the next steps so that we can address those, at least some of those questions in a finite time? I mean, preferably before I retire. So the thing is that we have to build a network of detector. That is absolutely important, because otherwise we don't even know the locations of the sources, events. We need to develop efficient techniques to extract the signs out of the data. Even though we have a lot of computing, it feels that we have an enormous amount of computing time and so on. It is absolutely not enough in order to get all the information that is already there in the data. And also the new technologies which have come, like machine learning, etc., we are doing it like in a very pedestrian way. If we use them properly, I believe we can do much better. Then follow-up of sources with electromagnetic telescope. This, of course, is the ultimate goal, but unfortunately, this has not happened at the rate we expected, and I will spend some time on that. So while we are making the network, we also have to improve the sensitivities of the instruments which are existing, which are upcoming, and then eventually enter the third generation. That is where we build probably bigger detectors. And also, the present detectors can go through a paradigm shift, like we can put cryogenic detector and things like that. Then we have to build instruments at different frequencies, most likely in space, and that is the next frontier. For us in the Indian context, the next major step is LIGO-India, but then we should also not forget that the space-based detectors, the era of the next decade is going to be dominated by that, and we should not just start thinking about it, we should start acting on it, and I will come to that. No, little later. It should launch before that. Is it still possible? Okay. So here is the network, okay? And you see that these two are the detectors which are the most sensitive right now. The Virgo detector has comparable sensitivity, but it has not performed according to our expectations so far. The Kagra detector is also is having technical challenges, and maybe it will come up at some point. LIGO-India, even though it is under construction right now effectively, has the potential to become as sensitive as the two other LIGO detectors, and if all goes well and we work hard and harder, then maybe the most sensitive detector in the world, because of the site, because of the enthusiasm, because it is going to be the youngest detector, so we will not make the mistakes which we have done before. So these all possibilities are there, but that does not mean that we have to be the best or something like that. It is part of the ecosystem, but we should make the detectors as sensitive as possible, and for these reasons LIGO-India can become the most important one, most sensitive one. Like the geo detector is also a very important detector. A lot of technology development which happens for the LIGO detectors actually happen in geo, and then they are installed in the LIGO detector. LIGO-India can play a significant role in that direction also. I'll come to that. So now, these are the sensitivities of the almost latest sensitivities of the LIGO detectors, gravitational wave detectors. You see that the sensitivities, so this is mixed with Virgo, so ignore these ones, and you can see that the sensitivity of O1 was here, then O2 is slightly better, O3 was quite significantly better, and now we'll see what O4 is, and we are, as you can see, we are almost close to the advanced LIGO, at least in the lower frequencies, the advanced LIGO design sensitivity. But here there are a lot of technical noises which are much more difficult to figure out than the fundamental noise sources like short noise, etc. I will not get into the noise sources today. And then this is the A plus design. You will hear this term A plus many times. So this is the advanced LIGO plus design. The hope is that LIGO-India is going to operate at that sensitivity along with the two other LIGO detectors in the US. Okay. Now, see, these are some, I thought that I will just show some of the back of the envelope calculations in case my talk is too boring. So this is how the number of sources events will increase with LIGO-India. So we have 3 detectors. So suppose you take only 2 LIGO detectors, then you add 1 more. So you get the increase in signal to noise ratio as a square root of 3/2. But then the volume increases as cube in distance. So if you have a certain sensitivity threshold, it will increase as 3/2 to the power 3/2. It's a nice number, which is almost like 2. But the actual improvement is going to be more than 2. I'll come to that. Now, then there is one more very important thing, which is called the duty cycle. So since the detectors are always plagued by transients, instrumental and environmental transients, we can only claim a detection when 2 detectors detect the same signal simultaneously with similar parameters within the 10 milliseconds or let's say within the light travel time delay between the detectors, which could be like 10 to 10s of milliseconds. So that means both at least 2 detectors have to be operating and sensitive at a given time. When you have only 2 detectors, I'm not considering Virgo and Kagra at this point, let's say 2 similarly sensitive detectors, let's take 2 LIGO detectors. The probability that both the detectors are on at the same time is pretty low, because 70% of time a detector works according to our experience. It could be actually even smaller, but let's take 70%. So if you take 70% square, it is like 50% of the time 2 detectors will operate simultaneously. But if you now add 1 more detector, 3 detectors, then the probability that at least 2 are operating is close to 80%. So that is a significant improvement. This improvement is why it is so significant. You'll come see later on. Now also there is this increase in localization area. Okay, decrease in localization area. It is increase in localization accuracy. That is a significant motivation for LIGO-India. Now again, in the back of the envelope, if you add 1 more detector to the network of the present network of Hanford, Livingston and Virgo, you get 3 more baselines, right? Hanford, India, Livingston, India and Virgo, India. And all of these baselines are on the average twice the existing baselines. So you can imagine that the insensitivity is going to, the angular resolution is going to increase at least by a factor of 2. But then the number of baselines also doubled, because there are 3 and now there are 6. So all these things together, the increase is actually more than a factor of 5. It could be more and less, but of that order. Okay, so these are the kind of back of the envelope estimate, and I'll show the implications later on. So this is a very nice cartoon to see how the angular resolution compare. So this green one was the first detection, and this is on the sky. This is the error circles contours on the sky. And as you see, if LIGO-India was online at that time, this would be the localization error. And you can see that this source, GW 170814 and 170817, at that time both the LIGO detectors and the Virgo detector was operating, which made these error circles much smaller on the sky. Okay. And this is like this, basically the GPS satellites, that if you have the satellite, then you can use the delay to triangulize and locate a source on the sky. Now this is, there is a paper written by some of my colleagues which did lot of numerical estimates of that. So this is a plot. So here on the right side, this is only Hanford Livingston, and on the left side they have put the Aundha detector. So because LIGO-India is going to be located in the Aundha region of Maharashtra, this is now marked by A, and you can see that this is the localization area in square degrees. So this part, you can see that mostly it is in this region, that is like tens to tens of square degrees with only two detectors, Hanford and Livingston. Here, this is in this region, which is like 1 or few degrees. So you can see that that order of magnitude estimate is kind of holds. It is few times more precise in localizing the sources. Another way of looking at it, that what happens when you add a detector is this way. So this is basically done in a different context of stochastic background and so on, but this gives a very nice visual way of kind of representing what happens when you add more detectors. So this is like the point spread function when you have only two detectors, Hanford and Livingston. But if we keep adding the other detectors, this is Virgo and LIGO-India, you see that these sizes become smaller, and also eventually one will combine them, so it will become much narrower. Plus, you see that the coverage improves. So here you see that there is lot of error along this direction, but the error is smaller along this direction. So this is diffraction limited, but this is much worse than that. But when you have multiple baselines, this coverage is basically done uniformly. So you are scanning the same point on the sky with different beams, which are good in certain one direction but not in the other. But when you combine the results, you get much better, smoother sky coverage. So this is another way to look at it, using the standard deviation of multiple expansion. So basically this is the spherical harmonic moments. You see that these are the errors of different spherical harmonic modes with Hanford, Livingston and Virgo, three different baselines. This we did not reproduce for the Indian detector. But when you combine all three, this black line, so this is basically turning black into three different colors, but this becomes much smoother. So the thing is that once the error went down, the variance is low. Two, the fluctuations are much smaller. So it is a much better sky coverage. Now what do we do with all this? Now I said before that with LIGO-India we will be detecting at least twice more events, but it is actually more than twice. So this plot is basically showing that. So here first, this is the O3 sensitivity. Now we are better at O4, and this is the LIGO A plus sensitivity where LIGO-India is supposed to operate. Okay, and these are the third generation projected sensitivities, which will come later on. Now if you look at this plot, we are here somewhere, okay, and this is at the center, and this is with respect to Earth. As we are going back, radially basically we are increasing, we are going to higher and higher redshift. This left hand side is for neutron star binaries, and the right hand side is for black hole binaries. With the A plus sensitivity, you see we are almost covering a significant number of black hole binary mergers in the universe. Now if in the co-moving volume these events were uniformly distributed, then LIGO-India with LIGO-India, with the two other detectors, with the extra reach, we would see only twice the number of sources increase in the increase in number of the events would be twice. But because a lot of events are at higher redshift, let's say redshift of 2 and 3, the increase will be even more, not just 2. Okay. Now, but anyway, whatever it is, the number is pretty large. But then on the neutron star front, we are not doing very well. We really have to go to a third generation detector. This green one is Einstein telescope, and this other one is Cosmic Explorer. But then there is one more thing. There is Voyager here. Okay. With Voyager, we may be able to get a little bit of well, some more neutron star, binary neutron star mergers, which may be about enough to give us, to break the Hubble tension, which I will come little later. Okay. So now the thing is that, well, yes, we have to detect so many events. So that is good, and we are already detecting. But then there are some subtle things which are missing, and this is kind of related to what one of my PhD students does. See, this is one of the primary fundamental questions, that how the black holes form. So there are two competing models. One is a formation in an isolated scenario, like this binary goes through a common envelope evolution, and then at some point hopefully this envelope goes away, otherwise they merge much earlier. If they go away, then this star becomes a black hole, and then the black hole merges. This is one scenario. In this scenario, since this system is evolving together for a very long time, the spins tend to align. But then there is another scenario where the binaries are in a dense environment like globular clusters, where they basically there are three body interactions through which there is mass segregation, and all these heavy black holes come close to the core of the cluster, and at some point they merge. But because there are three body interactions involved through which these systems lose energy, their spins are not necessarily aligned. So the point is that if we could measure the spins of these individual black holes, we could say that how where they form, or at least like even if there is a mix that some form there and some from in the other channel, we could come up with the proportion that how this is happening. But the problem here is that if you want to search for this kind of precessing binaries, you have to use the spin parameters also for the individual black holes. The way the binaries are detected is something called the match filtering method, where we generate template waveforms for different parameters and then correlate with the data. If the cross correlation is high, then we claim a detection. But at this point, because of computational limitations, we assume that the spins of the binaries are aligned. That's a big assumption, because there is no reason for them to be aligned. You see that we assume that the spins of the individual black holes are aligned with the orbital angular momentum, and that can happen if they are forming in the isolated situation. And you would say, well, if isolated model is the right model, then this is a valid assumption. But how do you know that the other model is not the valid model? Because if they are precessing, you are not using the right template, we are actually not going to detect them. So there will be a strong selection bias which will say that yes, whatever we are detecting is aligned spin, but then you will never see the misaligned ones. But in order to do that, the number of templates which are needed and which is proportional to the computation cost is at least one order of magnitude. Okay, so don't get into all the numbers, but essentially these two you can compare, that this is for NSBH, but let's say binary black hole also. You see that about 10 times more templates are necessary. So how do you then estimate this, detect those sources? In parameter estimation, once they get detected, then one can do the parameter estimation and find that they are precessing or not. But the problem here, as I'm saying, is that we may not even detect the most interesting ones. So one way to do it is called hierarchical search, and I will just summarize it here. I have many slides, but I will not get into this. So this search was proposed long time ago by Sanjit Dhurandhar and his students, but in the past few years what we have done is that we have made it applicable to data and addressed all the intricacies that has to be addressed first if you want to apply something to the data. Okay. So basically what we have done in summary is that we have applied this method to the data and recovered all the sources that were detected in what is called the gravitational wave transient catalog, which lists all the sources, and almost at the same sensitivity, same significance, with factor of 20 speed up. Okay. So what it means is that we can now, we should be able to include more and more parameters to do these other kind of searches. Now there was one issue about the how you estimate the significance and so on, which also we have recently addressed, but I will not get into that because then it will take much longer time. I will come back to the slides if you want later on. Now moving on, so there was the next, probably some would say the most interesting event that happened was GW170817, which was a binary neutron star merger event which was followed up by a large number of electromagnetic observatories in the world. And many Indian observatories also participated in that activity, even though, for example, AstroSat did not detect it. That non-detection, because it was sensitive, that non-detection helped us in localize the source. But anyway, so coming back to the main point here, the thing is that, so this was the first this thing by gamma ray, GRB and LIGO. So the primary localization was given by the gravitational wave detectors. So you will see this animation is unfortunately a bit slow. So that will come here. Now once that was done, then you have to look for a kilonova or some in optical, okay, which happens after some time. Now, so once that is detected, one can do all kinds of spectroscopy and also get the redshift, from which one can then estimate the Hubble constant. Okay, so yeah, I think this is the main essence of that. Now, what did we learn from this event? So there were, even though it was just one binary neutron star merger which has been followed up, it gave a huge amount of signs. All these things that binary, this BNS GRB connection, which were theoretically postulated, could be verified with this. This was the first direct demonstration. Then that the indication of heavy element formation in these events, like that gold, etc., which were highly publicized, those things were measured. And then so that we also saw that the neutron stars equation of state is softer. That is, the stars are more compact than this thing. So all those things were done. But the primary interest I have was in the Hubble constant. So this measurement gave another handle on the estimation of Hubble constant. And as you know, that there are two groups of measurements of Hubble constant by Planck and then supernova surveys and so on, and they don't match. There is a gap there, and one of them or both of them are wrong. Now, with an independent handle, we may be able to break this degeneracy at some point. There was a paper which was written by Daniel Holge and his group, which said that we may be able to reach 2% accuracy estimation of Hubble constant in the next few years, which did not happen because after that there was no follow-up of binary neutron star. But now we wanted to check that what is the actual exact implication of LIGO-India in this particular specific problem. So see, earlier you saw that there was this paper written where they said that how much would be the improvement in sky localization, etc. But we thought that we will rather ask these questions more directly. That, so this is the thing, that how many years we are going to save with LIGO-India in resolving Hubble tension. Okay. So basically what we do, we perform very realistic end-to-end simulation to see how many sources we pick up with LIGO-India and without LIGO-India. Pick up meaning, okay, let me explain what we are doing. So there is a simulation where a lot of binary neutron star signals are injected in different parts of the sky in this redshift range where it is still possible to detect. Then there is a low latency pipeline which basically detects potential signals that is run. Then there is that output is fed to something called base jar, which does this localization whenever there is enough strong signal. Then we tile the sky at that point using the tiling method which people are using for scanning the, covering the potential part on the sky. And then we ask the question that suppose we are given only one night telescope time, will we be able to detect the source or not? And that leads to this kind of results. This is very preliminary, so I would not quote this already officially. But what happens is that you typically need 50 binary neutron star follow-up to get about 2% detection. Now suppose there was like only one was detected every year with the HLV detectors. Then you will take 50 years to reach there. This is with current sensitivity. But if you use, so I should use A here, if you include the LIGO-India detector, then it takes about 30 years. This is that 60% or whatever improvement we got. So what does it mean is that suppose in this scenario it is about 17 years with when you do it proper precision, you save about 17 years with LIGO-India. So now this is with A plus sensitivity, but if the sensitivity is improved, so typically this is to get a good flavor for the numbers. So suppose with the present Hanford, Livingston, Virgo detectors, you could resolve Hubble tension in 30 years, then with LIGO-India we will be able to do it in 20 years. And that I think is a good number, again keeping in mind my retirement age, that it will, yeah.
That it doesn't signal new physics. What if the Hubble tension is real?
Well, it could be, but then we are not. See, the thing is that at least we should have another measurement in the low redshift universe. Suppose it is either consistent with supernova or not. So then, if it is consistent with supernova, then you know that there is a real tension between CMB and meaning high redshift and low redshift. So maybe CMB has a systematic effect. That is also possible. No. I think I'm saying that whether, I mean, if you go back to this, suppose the error bars, these blue are the error bars for LIGO. It shrinks and fall on top of the supernova one. Then it is basically reconfirming the supernova result, right? I mean, then at that point you have to believe the low redshift one. But suppose that,
right? But you mean you can believe the low redshift one for low redshift? And
yes, yeah. No. Right. I understand that. I then at that point. So then you know that supernova results are correct. Meaning, suppose both the results are showing the same region, then you know the low redshift measurements are correct. Then at that point you will have to go back and see whether the high redshift measurements have a systematic effect, or really the Hubble constant at higher redshift and lower redshift are different. So that will be the questions at that point. My belief, of course, is that there is a single Hubble constant, but that is my belief. It may be completely wrong. That maybe the universe is different at two different scales. Okay? Yeah. So now, So now the thing is that, so this is what I'm saying is that roughly 10 years is a good saving in this business. But then, if Virgo does not work, so this is with HLV and this thing. If Virgo does not perform as expected, then of course you can see that this 30-year could be infinite number of years, because it may never happen. Okay, so now I'll quickly go through one more thing, that these are the kind of discovery potentials with LIGO. Yeah.
Even LIGO need not perform. LIGO-India also need not perform.
We'll come to that later. That's a very provocative long answer. I think it should work. I mean, why it should not work? Two LIGO detectors in the US are working. We can make a man-made disaster, then it will not work, but otherwise it is supposed to work. Okay, so the thing is that this is also kind of interesting that what are the potential that more detectors bring. So you also see so far we have been talking about the inspiraling binaries, but we also made an estimate that what about the hyperbolic interactions of black holes? And you can see that, I mean, we put actually the most realistic simulations that were available, which took into account that, you know, how the black holes evaporate from not in that sense, black holes go away from globular clusters and things like that, all those things folded in. We estimated some of these things, and it turned out that with LIGO A+, there is a chance that we will be able to, chance is low, but there is a chance of, like, you know, 10% possibility of detecting this kind of hyperbolic interactions per year. So if you operate for 10 years, then there is a chance of seeing one. And if these are, since we are talking about the low, you know, the high, so what should I say, the tail of a distribution, the chances could be even more. But then our estimates are very conservative. And also it does not depend on the lower cutoff threshold of the SNR. So what happens is that in these hyperbolic encounters, the black holes, two black holes come very close and then go away like this. And then if you take a impact parameter around it, a very small change in the impact parameter can result in a very large change in the SNR. So if your detector cannot detect, let's say, SNR of 5 and it detects SNR of 8 or something, then there is a very small change in this angle. So the probability actually does not change much. So what I'm saying is that even though this probability looks low, there could be a pretty high SNR significant event if LIGO-India operates for 10 years. There are searches which are already going on. People have started developing templates, all those things for this. So this kind of discovery potential is also there. Now I cannot give a talk without talking about the stochastic background, because that has a major discovery potential with LIGO-India. So there is a stochastic background which is created by the distant and unresolved sources. Basically, it is like a box of crackers. You don't know which one is going when, but overall statistically some power is coming. I mean, most of the electromagnetic astronomy actually relies on a stochastic background. They are all stochastic. We don't say explicitly. We don't measure the phase of the light that is coming. Now for LIGO sort of instrument, how do you detect such a background? Because we are using detecting the phase. So basically, suppose you have the signal and noise, and if the two detectors are quite far away, then you can correlate the data from the detectors and assume that the noise is not correlated, and the signal will have some trace of this correlation. This is how a stochastic background can be detected. Now why it is important for LIGO-India, I'll come in a minute. The thing is that this is a very nice plot made by Duncan Mitchell in his thesis. So most of the detections that are happening with individual detections that are coming from this very low redshift regime. You see, this is the BNS, blue is the BNS and red is the BBH, these dashed vertical lines. But these other distributions are showing the distribution of those events that are happening in the universe, and this will appear as a stochastic background. Okay. So basically, a detection of stochastic background will tell us about this population at the higher redshifts and the individual ones at the lower redshift, and then we can see how to make a combined astrophysical model which can smoothly represent both of these. And with different parameters, you get very different background. Now what happens is that, so if you plot these backgrounds here and there, I mean just focus on this plot, let's say, that with as this is plotted with observation time in months. So basically here you complete about 3 years, okay. You see that one can make a 3 sigma detection with about 3 years of LIGO A+ sensitivity. These estimates have changed now, but it is of that order. Now this is my claim, this is not, okay, in this talk everything I'm saying is like my opinion, not the collaboration's opinion. So the thing is that what I believe, what can happen is without LIGO-India, one will probably cross 3 sigma, but with LIGO-India and with some more time, probably we can break the 5 sigma limit. So these kind of possibilities are there. It is sort of like the present situation of pulsar timing array. Now once you do that, then the thing is that if you detect something, with an isotropic background, but that background is actually anisotropic. One has to probe how anisotropic the background is, because otherwise the amplitude that we will get for the isotropic background will not be right. So the astrophysical parameter estimation would not be correct. So I will not get into this. Again, this is I love this topic, but I will get into some of the things. But so here, one of the important thing is that because I worked with on CMB with Tarun, a lot of techniques that are used in CMB were just readily imported here, and we wrote a series of papers on addressing many of these, like how anisotropic the background is, how they should be represented in spherical harmonic domain or pixel domain, in which situations, how do you deconvolve or basically put an estimate on the physical quantities, how if there are multiple components there, how do you separate, and all those things are there. And also we made now there is a technique which we developed called folding and so on. We could make maps at every frequency bin. That again gives us the possibility of making discoveries in the future, like if there is a single narrowband source which is there in the universe and we just don't know, it is not modeled. So these kind of things. Okay, I will for kind of see, ultimately we want to make maps like this. These are the maps of the sky in different frequency bins in electromagnetic astronomy, and we are right now here with some transients, not persistent maps. So this is literally a long way to go, but now I will come to the final few things, that what is happening later in the future, what is being planned, and how LIGO-India again can help here. See, these are the detectors which are planned for let's say 2040 or so. This is Einstein telescope, and this is Cosmic Explorer. Okay, these are all 10 kilometer, 40 kilometer sort of arm length. Now, LIGO-India is expected to start operating in 2030s. Okay, so after LIGO-India takes few years of observation, what happens is that LIGO-India can play the role that GEO 600 is playing for LIGO. So many of these research activities, many people are asking us that what is the research potential of LIGO-India? So we are getting basically a head start with LIGO-India installed here. Once it is installed, for all these third generation detector development, the all instrumentation final stage validation could be done at LIGO-India, and all these technologies could also be done by people who are working here. See, LIGO-India is not just the instrument, it is also the people, the community which will be created by that. And I will give you one or two examples, because otherwise it will not be convincing enough. So one of the primary noise sources that is going to be created, that will be a limiting source for the next generation detectors, is the Newtonian noise. That is, when the seismic waves are going through the ground, there are these ups and downs in the masses which are directly coupling to the mirrors. These cannot be shielded. The seismic waves, seismic noise can be shielded, but not the gravitational coupling, which is called the Newtonian gravity gradient noise. So what do? You can create put a large number of sensors around the detector, hoping that those sensors are sensing the seismic noise which is correlated with the data that we are receiving, and then use adaptive filtering to cancel out this noise. Now this kind of work was done by my student Nikhil Mukund and other collaborators, but you can see that this is the effect of LIGO-India. Because without LIGO-India, we would not get into this, and LIGO-India is going to create this kind of community, and this technology is going to be absolutely essential for the next generation detectors. And then he also did a lot of work with machine learning, not only for data analysis, also for the instrumentation, because people are getting into a lot of automation with the real detectors, that how the mirrors are pushed. So all these things are going to happen, and there is a lot of scope, and Tarun made this slide long time ago, that how various fields can contribute to LIGO-India. It is basically inherently a multidisciplinary mega science project. Okay, now finally, last few minutes I will spend on the space-based detectors, okay, because that is also, as I promised in the talk. See, there are different detectors which are being proposed by different countries and set of countries. So this is LISA. LISA is flying in 2035. There is a Chinese one, not sure when they are going to fly. And then there was a decihertz detector which has been proposed initially by the JPL group called the Big Bang Observer, but that was not funded. Then there is a decihertz interferometer gravitational wave observatory, DECIGO, which is proposed by the Japanese, but that is also not funded. So there is right now a window in the decihertz band. Now for LISA, there was a Pathfinder mission which was sent, and the performance of the Pathfinder, this was the requirement for the Pathfinder, this was the requirement for this, basically they wanted to test the drag-free environment. This was the noise requirement for LISA. The Pathfinder did already better than what LISA's requirement was. So this is clearly showing that these technologies are not science fiction, these are highly possible and these are going to happen. Now one of the primary selling point of LISA is that LISA is going to detect a large number of binaries well in advance. Okay, this will forecast that when some merger is going to happen. So these ones are going to merge in the LIGO band. Okay, because initially these binaries go slowly, and then as they come closer and closer, their frequency and amplitude both increase, which is why they are called the chirp signal. Now when they come, so you see that this is typically a few years. The early alert for LISA will be in few years. That's a bit of a problem, because LISA is flying, let's say in 2035, but then these other ground-based detectors is not clear how many of them will be working, especially if LIGO-India is going to work at that time or not, what will be the future, and you have to wait, after LISA you have to wait for a few years. So it could be like 2045 or something we are talking about. That I am certainly going to retire by then. So that is not acceptable. But then there is this gap here. You see that there is a decihertz gap. Now there are two things there. You see here, this is 1 hour. So if we have a detector in the decihertz band, we could make a prediction, forecast few hours in advance to few minutes. That's very nice. Plus, if you have a decihertz detector like this is something called the Tiango detector, which was proposed by Caltech and Chinese groups. And these are the sensitivities of the ground-based detectors. And this is the decihertz detector. You see that there is a overlapping region. Okay, that is, a decihertz detector can work together with a ground-based detector. If the decihertz detector is million kilometers away, then we get a million kilometers baseline, which gives enormous like orders of magnitude improvement in early warning and localization. But I'll show you this curve, which will make the idea clear. So with all these combinations, with these ground-based detectors, this is the error in Hubble constant, and this is omega matter. Okay, if you include this red one, that is this space-based detector, along with these detectors in Voyager configuration, we did not talk about it, but LIGO-India can get into a Voyager configuration, which is like the 2.5 generation. Then this error bar becomes this small. Okay, we certainly bake this degeneracy with very high accuracy, which is much faster, and with spending much less amount of money. And not only this is going to do this, but it can actually do the variation in Hubble parameter also. This is redshift, and we should be able to observe how the Hubble parameter is varying with redshift. So which can then tell us about dark energy and things like that. Now there is one more motivation for a decihertz detector, that it is believed that in this decihertz band there is a certain window through which we may be able to see the primordial gravitational wave background, which was created during inflation, and that will be another exciting thing. But then there will be all kinds of foreground issues. I don't want to talk about this right now, but all these measurements, the stochastic background measurements, etc., which we are doing with LIGO-India, or which we will be doing, those things can help us in finding out the background contamination. See, ultimately this is the cosmological stochastic gravitational background, and you see that there are many other things there. I mean, not exactly that, but certainly this thing is there. Okay, so if we have to make a measurement, of this one, we have to remove all these foregrounds. But how do you remove foregrounds? It's exactly like, I mean, I think it will be exactly like in CMB, that you measure the foreground where the foreground is the strongest, and then extrapolate it back, and then remove this whole line out of the spectrum, and then maybe at some point we will be able to reach there. Okay, I will. So there are, for DESIGO, people did estimate that it may be able to touch this inflationary background, but DESIGO was a bit of a complicated design. It had Fabry-Perot, and it was a triangular design and so on. It may be little more complicated, but what we are thinking about is basically put a LIGO in the sky. 3 detectors, may not even be a Michelson interferometer, may not have a Fabry-Perot cavity also, just a simple Michelson with 2 mirrors and a beam splitter, and that can reach pretty good sensitivities. So you see that with 1000 kilometers or 100 kilometers, the sensitivity is not that bad. Of course, the science outcome will be a little compromised, but these sort of things are possible. But then if you put some kind of a little bit of a cavity with some finesse stain and things like that, then it goes a little better, but then not that bad. I mean, anyway, so all these things are going around. So I will end with essentially saying this, that with LIGO-India in the horizon, and we need to think about the next steps. Getting land for 10 kilometer or 40 kilometer detector is absolutely, I mean, almost out of the question. Okay, let's say that this is not going to happen. Then LISA has gone way ahead right now. I think our best bet is decihertz. Otherwise, we'll have LIGO-India and no next step, which is not a good situation. Okay, so I will end here. So the first detection marked a grand beginning of gravitational wave astronomy. But then with all the exciting science that has come out of it, it is still the very beginning. But the promise is enormous, as we can see over the last few years. And that is why worldwide effort is going on to improve the sensitivities of the present detectors, make a network of detectors, go to space and all those things. LIGO-India is like to play a major role in gravitational wave astronomy. I mean, it is going to save years of this thing in many ways. And also the community which is going to be built by LIGO-India is going to contribute to instrumentation and theoretical sciences, which is a very significant thing and probably the most significant contribution to this. This is after all science, it is driven by people. And finally, the decihertz band promises breakthrough science, and there is no approved missions yet. With the present reputation of India in gravitational waves, hopefully if we do LIGO-India properly, and with whatever we have done so far and the space missions that we have done so well, decihertz is certainly the best, the next step to take. Okay, I'll stop here.
Just a simple question. The decihertz, what is the size of the arm length?
So you can choose the arm length. This is here so these two plots are for 100 kilometer and 1000 kilometer.
Okay, so it will be much, I mean, technically much simpler than LISA, is it?
Yes, it is technically simpler than LISA. LISA uses a different technology. Here, see, LISA has gone quite a bit ahead. I mean, right now we can contribute components of LISA, but we are not in a position to lead it, absolutely, I mean, late. But here the thing is that it is almost like flying a LIGO to the sky. So assuming that we will know how to do ground-based interferometry, and if we can do certain amount of automation, those work anyway we are doing, that how to lock an interferometer without touching it, that is artificial intelligence or machine learning based. If those kind of things we master, then this will become a pretty interesting thing. This also becomes interesting for the space organization, because this requires flight formations. 3 different spacecraft for doing a flight formation is pretty exciting, I think, and we got informally we know that this will be quite exciting there.
Thanks for the nice talk, and I have 2 questions. I'll ask the first one. What kind of early warning we expect from the decihertz space?
Yeah, so this is about an hour to few minutes. So you see that, okay, let me show this plot, other plot. So this is the thing. See, this is the early warning plot. You see, this is time to coalescence. And as the time increases, you get better and better sky localization. But then if you wait for too long, then there is no lead time remains, right? I mean, so this is the angular uncertainty in degree. Two colors represent two different distances. If the source is at 50 megaparsec or 200 megaparsec, and you can see, let us take the 200 megaparsec one. So you see that you within like a month before or 2-3 months before, you reach 10 to the power minus 0.01 square degrees. So it is pretty good in localization. But this could be, like optimally oriented and things like that. So it can be little worse, but of this order. This is because of this enormous baseline length.
Okay.
The Desihertz detector is operating along with the Earth-based detector, but that detector is spaced 1 million kilometer away. So you are using this million kilometer bandwidth. Right now with the like Hanford, Livingston and Virgo, it is like 1,000 kilometer baseline.
So another question is a curiosity question. I was wondering, this Einstein telescope seems to be a more stable configuration because of the multiple detectors. So why was that not thought about in the first place when the LIGO was conceptualized? Such kind of a configuration.
The thing is that it is fairly complicated, and I am not sure, like, we will see how it progresses and what finally comes out, because Einstein, I mean, we have to, so LIGO, I think historically chose the simplest design that we can operate. Like the mirrors are not cryogenically cooled, it is not underground, and people could ask the question that why you are going for such a simple thing. But the problem is that these detectors are very complicated, and when multiple subsystems work together, it becomes very difficult to debug. That what is going wrong becomes very difficult to identify. I mean, you can see that even though the Japanese detector is slightly more complicated than the LIGO detector right now, they are having quite a bit of challenge.
So I noticed that if you increase the arm length, your sensitivity, space-based detectors I'm talking about, the sensitivity increases quite a bit. So I was wondering what puts the constraint on the arm length?
Okay.
Space.
It is so sensitivity does not increase. Actually, you see that it goes higher and higher. So it is actually reduces, but the constant
No,
is.
but the other plot you showed after this.
Oh yeah. No, that is so there is laser power and these things are involved. Yeah, you are right. The bandwidth. Okay, so there are multiple things which operate. I'll tell you the actual how the sensitivities comes. So this is like slightly like this thing pedagogical, but this is like this. So suppose you have an interferometer and a gravitational wave is moving past, okay? So the mirrors are moving because of that. Now you are sending a laser light, it is hitting the mirror and coming back. Now what we are saying is that this time scale is much shorter than the gravitational wave time scale. But now suppose that this light is actually going several times to the extent that the mirrors have started becoming, the phase of the gravitational wave has changed. If that happens, then you start losing the signal. So typically the length of the detector is, optimal length of the detector is λ/4. So which is why the LIGO detectors are, LIGO detectors does not look like that, but it is actually 1,000 kilometers. LIGO detectors have this finesse, which is of the order of 300 into 4 is basically, it makes it a 1,000 kilometer detector. The wavelength that it looks at, it is of that order. Basically, you could say 750, but then there are some other factor, etc. But it is basically of that order.
Okay. Thanks.
Yeah.
It was a great presentation. I have a question about the problems that you said the Virgo detector is kind of facing, and how is that sort of informed sort of the design or the working of LIGO-India? Like, are there some lessons that you would,
So I did not, the Kagras thing is basically they wanted to use, I mean, I don't know, I think, I'm not sure whether these are publicly this thing, but Kagras problem is related to the mirror material that was used. They wanted a cryogenic detector, they used sapphire mirrors, and then I don't know all the technical details, but apparently, so there are some issues they faced. For Virgo, it was not, it is not very clear what is wrong, let's say. I mean, it is like these are humans play a very important role in all these detectors. Human component is also another big component. 90% component is human. And humans are very complicated to understand. That is the problem. This is recorded, no?
Any other questions? I just had a quick one. So you mentioned about the rates of BNS mergers, and we have had one electromagnetic follow-up. Do we understand why the rate is low and there has only been one instance?
The thing is that it is the other way around. People came up with the rate based on that detection, the first detection. But that was, I mean, it's like one detection, really you should not estimate rates based on that. Right now, it is not very clear what are the rates of binary neutron star merger is. So then when I talked about these simulations, it is basically saying that we will detect one BNS event per year with the A+ sensitivity is just like an anchor. We will shift that, but this is just to show the proportionality. It is not clear that why, I mean, I think we will need, by the way, but one thing is that LIGO did detect more binary neutron star mergers, just that they were not followed up. That improves the rate, but that's where it is. So the rates have become little more tighter, but it is very difficult to say how many we are going to detect.
So in one of your earlier slides, there was a list of unanswered questions. You had mentioned about this neutron star matter. I'm just curious to know how how this helps to understand.
Yeah, so the thing is that, let me see. So, okay, let me just say this thing, that the waveform that you saw, that the waveform that is generated by these binary neutron stars, that waveform gets distorted when there is a neutron star present, because the tidal interactions affect the neutron star based on their equation of state. This is measurable effect. So then that can go in there. With LIGO-India, I believe, I have not looked into it carefully, what happens is that the orientation of the source, etc., will be very precisely determined. That will remove a lot of degeneracy in the parameters. So I think these parameters, this tidal deformation parameters of the equation of state, those will be better estimated with LIGO-India.
So we could decide whether it's a softer or is there further we could do?
So I mean, I don't know how many. See, the thing is that people can put more parameters, but then I think it will become weaker constraint. I don't know exactly that how well. See, if you see these plots, usually there are this whole bunch of lines of this mass versus radius plots. So it is like this inflation, like thousands of them are there. So I don't know how well we will be able to finally constrain with these measurements. Maybe with third generation detectors, when we detect this whole bunch of them, maybe something better will come out of this.
The other thing to say is for neutron stars, we are more interested in high frequency end.
That is
A detector which may not do very well at low frequencies.
Yeah.
But make sure that you can do the other part well, which is squeezing and everything.
Yeah.
Get the photon short noise. Then like Nemo is trying to do. Then you will go for, you're gunning only for the neutron star.
Yeah. So there was a detector which was also being conceived like this, called Nemo detector. Maybe it is still there, but it is, so this detector was focusing on the high frequency part of the spectrum. So there basically when the neutron stars merge, there is a what is that called? Something. So so it basically it is a metastable sort of state of neutron star which is formed, and then that by looking at that you can get these high frequency modes which can tell you more about the neutron star equation of state. But there, I think I would suggest that you invite some real guy who works on, like, neutron star equation of state and so on, who will be able to give you better details. Yeah.
Sorry, I'm indulging myself to the last question. What, if you could maybe touch on what status like LIGO-India is in right now? Like you mentioned, like observations to begin in 2030, but it's been a few years since the.
It's progressing.
Oh, okay. But on the ground, are there like boots on the ground? Like, is the construction happening?
So there is, so there are fence. Yeah. So I mean, so there are some public document you can kind of see what is the current present status, but it is like there is a site office right now, and then things will happen hopefully on time.
Any further questions? If not, then let's thank our speaker once again. Here's the small token from us.
Oh, thank you.
Thanks everyone. We have refreshments outside.
All right. I know. I mean, what to? Hey, by the way, the recording is stopped. Recording has to be stopped now. Right? It is stopped. Stopped already. Okay.